In this video, we're going to take a look at using Microsoft Excel to do some of the calculations related to probability. So I want to start with this problem up here at the top. It says to find the expected value and standard deviation of the following discrete probability distribution. And this is the probability distribution borrowed from an earlier video where we were talking about x was equal to the number of siblings of some students in a class, and this was the associated probability of picking out a student with that many siblings. So this is from a problem that we did on an earlier video. Finding the expected value and finding the standard deviation are going to require us in Excel to unfortunately have to go and use the actual formulas for those two quantities. There's no magic shortcut to do these types of problems here. So I'm going to kind of skip back and forth here between my tablet version so I can write down what those formulas are, and then back to laptop version so I can type in some values over here in Excel. So let me just write down what the formulas are that we're going to need. So you'll recall that mu sub x is the notation we use for the mean or expected value of a probability distribution with random variable x, and sigma x is the standard deviation of that same thing. So if you look at mu sub x, the formula for this is we sum up all the x values times their associated probabilities, p of x values. And for the standard deviation, we're going to have to first find the variance and then eventually take the square root of that variance. And so there were two different formulas for the variance that we looked at. I'm going to select the slightly easier one, I think, in my opinion. That is, we take the value of the random variable and we square it. We multiply that times p of x, and we sum those all up. And then we have to subtract off the square of the expected value that we found before, and then take the square root of this whole big ugly mess. So these are going to be the two different formulas that we have to use. So let's come back over here and see how we can find each of these quantities using some basic formulas by setting it up here in Excel. Okay, let me reorient my computer here. Okay, so I'm going to start with the expected value, the mean right here. The first thing we need to do is find the product of every single random variable and its associated probability. And so what I've done is I've already typed in the corresponding x and p of x values from this table. I've essentially just copied these values into two different columns in Excel. In this next column, I want to write down the product of x times the p of x. This is what I want to do. I want to take this value and multiply it by this value, because that's what we need to do according to our formula. We take the product of those. After I've taken the product of those for every single one of these pairs, then we need to sum them all up. So to do that here, I'm going to have to use formulas again, and I'm going to start by typing the equal sign. And we have a couple of choices. What I want to do is take the value here in column A and multiply it by the value in column B. Right now the row I'm in is row 2, so I want to take A2 and I want to multiply that by B2. So basically I'm taking this value and multiplying it by this value. And again, using this equal sign, it'll allow us to do a formula, even if it's a formula of our own creation, which is essentially what's going on here. And so if I just take that product of those and hit enter, it will sure enough give me the product. 0 times 0.3 is still going to be 0. Now instead of having to go and manually type that same thing for these remaining ones, if I just click on this and I go down to the corner here where it has the little dot and hover over it, my cursor will turn to a plus sign. And if I click and drag down, what it'll do is it'll basically copy that formula that I just did, and it'll intuit that it knows in this row we were in row 2, and as we drag it down, it'll know to use, I want to use the values in row 3, the values in row 4, the values in row 5, and sure enough, you can verify. 1 times 0.35 is going to be 0.35, 2 times 0.25 is going to be 0.5, 3 times 0.1 is going to be 0.3, so you can verify that, in fact, all of those worked. So if I want the mean now, So if I want the mean, all I need to do to that list is take their sum. So again, I can do equals sum. I'll use the sum command and do a parentheses, and now we just need to tell it what to sum. And I need to sum up all of these values. So I want to go from there down to there. So I can just drag and cover them up, hit enter, and it will spit out the mean for me. So the mean, see if I can write this here, is 1.15. And that should be the same value that we found by hand back when we did this problem sort of out by hand. And also if you use the TI-84 calculator or similar calculator, you'll get the exact same value. This formula is going to be a little bit more complicated. So looking at this formula, I'm not going to use x times p of x, but instead I have to use x squared times p of x, but we can still do that. So that's what I'm going to do. I'm going to start by taking x squared times p of x and generating a row of values just like I did here. So let me just type here what I'm going to do. Here I'm going to do x, and this little up arrow caret, it's the shift number 6 on your keyboard. I'm going to write that as how we're going to write the square, and I want to take it, so x squared times p of x. This is the notation that I'm using. And so basically this little caret is meant to represent exponents. The idea is that it's kind of pointing up, and that's telling us that this 2 is kind of up. It's a superscript there in the place where the powers normally go. When we write out our formula, well, it'll actually look fairly similar to this. So I'm going to hit equals. And again, I want to take the value that's in the row of x, and I want to square it. So in this case, that's column A. I want to take the value in column A and square it. So in this case, that's A2. Oops, A2. And I want it squared, so I can do that same caret. I can do up to that power, and that will take that number and square it. Then I want to take that result and multiply it by the value here in row B, so times B2. So this is what my formula looks like. I'm going to take A2, I'm going to square it, and then I'm going to multiply that result by B2. And if I hit enter, it'll spit out the number. And again, it makes sense. 0 squared is still 0. When I multiply that by 0.3, I will get 0. And we can do the same thing we did before. If I click on this entry and go down to the right corner where it says plus, I can now drag down, and it'll apply this same formula to all the other rows. And so it's gone ahead and done that. And we can again verify 1 squared is 1 times 0.35 is still going to be 0.35. 2 squared is 4. 4 times 0.25 is going to be 1. 3 squared is 9. 9 times 0.1 is 0.9. So indeed, we've got all of those values according to this formula, where we've squared the number here and multiplied it by the number here. The next step, so we've taken care of everything inside these square brackets. The next step is going to be to take that list of numbers and add them up. So I'm going to do the same thing that we did here. I want this to be the sum of these values. And I'll close my parentheses, and hit enter. And now I've got this portion of the calculation done. So basically this portion here in our example just turned out to be 2.25. Next thing I need to do is subtract off the square of the mean that we just found. So I already found the mean, it's right here. I need to subtract off its square. So I need to take this number and square it and subtract that result from this number. And that'll give me everything over here in this formula except for the big square root. So we can do this in a couple of steps. We can do it all in one step. Depends on how we want to do it. So if we want, I can write this in one formula. So let's do it down here. I want the standard deviation of that list, of this probability distribution. So to do that, I'll do it in this square over here. Again, I'll start by typing my equal sign. We're going to do a big formula. And the command to take a square root is sqrt. That is how you take a square root in Excel. So sqrt. And what are we going to be taking a square root of? Well, let me put my parentheses there. type in the value that we want. So I want to take the square root of this number that we just found. That's the number in, I can either just copy it in and type it in by hand, 2.25, or I can refer to this position. It's sitting at D6. So I'll refer to it that way. D6 minus this number squared, which is the number sitting here squared. So that is in C6. So minus the value in C6 squared. And I'm doing this all in one step. So it's going to take the 2.25. It's going to subtract off this number that we know is 1.15, but we need to square it. So this is the 1.15 squared. And if I just hit enter now, it spits out our answer. So this answer turns out to be 0.963. And incidentally, if instead of using that formula, if you just wanted at this point to use these numbers that we found, you could do it that way as well. So I could just manually do square root of 2.25, just type that number in instead of referring to it as D6. I could just copy the number in, minus 1.15 squared. And it'll give us the same result. Oops, I guess it won't give us the same result. It's not letting me do that. I guess it really does want me to type in those values. Well, I guess I lied. I thought we could just do it by manually typing it in. I guess you could do it in a calculator if you want, but I guess you need to actually refer to them by their positions in the square as opposed to just typing in the numbers. So 2.25, instead of typing in 2.25, you need to type in D6, the location it's sitting at. And instead of typing in 1.15, you need to type in C6. I'm sure there's a way to get around this. I'm just not an Excel expert. So if one of you knows better and knows a way to type in the numbers themselves as opposed to references to their position, then you're welcome to do it that way. I'm not a super expert on Excel. Okay, so here are our two numbers, the mean and the standard deviation. And here was sort of a guide for how we get this other big ugly number that's in this formula. What if we wanted to do this other problem? This is a problem from section 6.2 where we're talking about the binomial distribution. So this is a binomial distribution problem. And it turns out that these types of problems are a little bit easier. So this one says a basketball player is an 84% free throw shooter. In a given game, they shoot 10 free throws. We went through the discussion of why this represents a binomial distribution in the video about using the calculator, but I'll just go through that again here now as well in case you didn't watch that video. But the idea is we want to make sure that this checks off the 5 conditions required for something to be a binomial distribution. The first criteria is that we have a fixed number of trials, and in this case, we've specified this person is going to shoot 10 free throws. So if we go through the requirements, requirement 1 is fixed number of trials. And in this case, we've got 10 trials, so we absolutely have a fixed number of trials specified. The second condition is that there's only 2 outcomes. And sure enough, when somebody shoots a free throw, there's only 2 outcomes. They make it or they miss it. So we will define a make as a success and a miss as failure. So make is equal to success. 3 and 4 we'll get to in a minute. But this means the fact that we've defined making a basket as a success, that needs to be how we define our random variable. So x needs to be equal to the number of successes, or in this case, the number of makes. How many shots they make. And so if we define our random variable this way, if we let x be the number of made free throws, we're down to these last 2, which ask, in the case of number 3, is the probability of a success always the same? So in this case, the probability of the make, always the same. And are the trials independent? And this is where you can have a big discussion about the game of basketball. Is the probability of making a free throw always the same every time you go to shoot. So we're assuming this person's in an indoor gym, right? They're playing inside at a game. There's not like a nice calm day at the beginning and somehow like a windy storm at the end that's going to affect their free throw percentage. And what we're going to assume is there's also no such thing as a hot streak. And this is something that there have been studies that have largely shown that the idea of hot streaks is, in a lot of ways, it's a myth. They occur. We see what we think of as a hot streak, where somebody, gets a bunch of consecutive hits in a baseball game, or they make a bunch of shots in a row in a basketball game, something like that. But it turns out those types of events occur with about the exact same frequency that you would expect them to occur totally by chance. So we are going to assume, and again, this is an assumption, we're going to assume that the person taking this free throw always has the exact same probability of success, that every time they go to shoot a free throw, it has an 84% chance of going in. And that means we are assuming the trials are independent. Whether they made their last shot has no bearing on whether or not they'll make their next shot. So I'm going to assume that both of these are satisfied. We've seen that these two components are often tied together very closely. And again, I mentioned this in the video on the calculator. But I do want to highlight, this is one context where we can talk about how these things are a little bit, having one doesn't always imply that the other one will automatically be satisfied. So let me give you an example of that. Let's say we have the same scenario, but instead of one basketball player shooting 10 free throws, we have 10 different basketball players each shooting one free throw. So we still have a fixed number of trials. We're going to count how many shots they make, and there's still 10 because there's 10 people each shooting one free throw. There's still only two outcomes, make or miss, so success or failure. We can still define our random variable x to be the number of makes. And the trials will be independent. Whether or not the last guy made his shot has no bearing on whether I'm going to make my shot. And whether I make my shot has no bearing on whether the person after me is going to make their shot. So the trials are still independent, but the probability of success is going to be different. I'm terrible at shooting free throws. My probability of success is 10% or something like that. Whereas maybe the person before me and the person after me are good free throw shooters, and they're going to make 60 or 70 or 80% of their free throws. So each person has sort of a different probability of making their free throws. So this percentage is going to vary for every single player. So we can satisfy conditions 1, 2, 4, and 5 while still failing to satisfy 3. So 3 and 4 are often very closely related, but they aren't the same. That is an example where 4 is satisfied, but condition 3 is not satisfied. Okay, so after all of that discussion, let's get back to how to actually do this problem in Excel. So we've decided that this is a binomial distribution. We're going to be able to use the tools of a binomial distribution to answer the questions. What is the probability that they make exactly 8 of their shots? So what we need to think of are the 3 different pieces of information that are required when we have a binomial distribution, which this is. So this is binomial. We need to have 3 pieces of information. We need to have n, which is the total number of trials. In this case, that's 10. We need to have p, the probability of a success for one trial. In this case, this person is an 84% free throw shooter. So they have an 84% chance of success. If I write that as a decimal, that's 0.84. And lastly, we need to have the value of interest. What is the number of successes we're interested in? And then based on question A, we're interested in the probability that this person makes exactly 8 of their shots. So the last value I need is x, which is 8. And we're going to plug those values into, again, the formula looks like this. And choose x, p to the x, 1 minus p to the n minus x. And so we'll just plug those values into this. But in reality, we're not going to actually plug them in. We're going to do this problem in Excel. So let me come over here to Excel and see if we can answer this first question. So let me zoom out so we can kind of have the whole thing on the screen at once here. Good enough. So I want to know the probability that they make exactly 8 of their shots. If I come over here to Excel, so we're going to do part A here Maybe we can do part B here and so on. I'm going to hit the equal sign to start writing a function. And the function I'm going to write is binomial. And as I start to type in binomial, notice it starts to provide a bunch of options. And if we select this one, binom dist, with a period in it, that will work. But so will this other one, binom dist, without the period. It doesn't matter. So I'll just do this one, binom distribution. And it's going to require, if we click in here in the parentheses, you'll notice it'll tell us what we need. And we need 4 different things. We need the number S, trials, probability S, and the word cumulative is asking, is this, I'll get to that in a minute, but basically, is this a cumulative distribution or are we just looking for one value? So the number S is the equivalent of what we're calling X. So for us, that's going to be the 8. Then I'm going to put the number of trials, which for us is 10. And then I'm going to put the probability of that success. So the number of success, number sub S stands for number successes. We were interested in 8 successes. Trials was 10. We're at the third one that asks for now the probability of success, which is 0.84. And lastly, when it asks whether or not this thing is cumulative, we're going to put either the word true or false here. For this case, I'm going to put false. I do not want to treat this as a cumulative distribution, and I'll talk about what that means in just a minute. So then I'm going to hit enter, and boom, it spits out the number that we're looking for. So this is actually very similar to the functionality on the calculator. So again, I'm going to go on Excel, and I'm going to, let's do it over here. I'm going to do, doesn't matter if it's lowercase or uppercase, binom period dist. It'll ask for X, N, P, and then basically, do we want it cumulative? Which I'll just abbreviate like that. Okay, let's zoom in here a little bit. So we entered 8 was the value. Sorry, I'm writing with my screen open. It's a little tricky. 8, 10, 0.84, and false. We do not want it cumulative. We don't want it cumulative because the idea of cumulative means instead of asking what's the probability that they make exactly 8 of their shots, we would be asking what's the probability that they make 8 or 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0. All the numbers up to and including 8. And that, in fact, is what we're going to ask in part B. This is an example where we would want to use a cumulative distribution. We want the probability that they make 8 or fewer of their shots, so meaning 8 shots or 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0, and sum all those probabilities up to give us this big combined probability here. So using false means we are interested in only that one exact outcome. If we use true here, that's the only difference that we'll do on this next problem. So we'll see that in a minute. But let me just write down the answer. We got 0.286. We'll call that, we'll round that up. What's the probability that they make 8 or fewer? So same thing, I'm going to come down here and I'm going to start by typing equals binom, and it'll give me some options for autocomplete, binom.dist. And let me just check and make sure. What if I don't do the dot and do this version of binom dist? So this is the old version. Let me just verify that it has the exact same commands, and sure enough, it's asking for the same things. So it's calling it for the number of, asking for the number of successes, the number of trials, the probability of success, and whether or not we want it to be cumulative. So you can use it with the period or without the period on that binom dist. So again, I'm interested in 8 out of 10 trials being successes with a probability of 0.84. And now I want to use true, because in this case, by using true, it's going to give me the cumulative probability of making 8 or 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0. It's going to add all of them up for me automatically, so I don't have to add them up myself. And I will hit enter, and there's that combined probability of all of those. So this is going to be the exact same thing, binom. In this case, I didn't do the period. I did binom dist without the period. You can do it either way, with or without the period. It doesn't make a difference. And it's the same values, 8, 10, 0.84. But now we use true in a case like this. So up here, this was a case where we had it exactly equal to a given value, and that's where we used false. In this case, we want it in the case that we have less than or equal to a given value. So less than or equal to 8 in this case. So here it was we were interested in the probability of having exactly equal to 8 successes, and here less than or equal to 8 successes. In part C, we're asking what is the probability that they make more than 8? Well, in this case, there isn't necessarily a built-in command that's going to do this for us, but we have to use a little bit of clever reasoning and recognize that when it asks for what's the probability of more than 8 is the complement of 8 or fewer, and we can do that on our number line here. So if I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 as all the possible number of free throws that they could make, in this case, we're interested in what's the probability that they make. Let's try to get this, try to get this all on the screen at once. Hopefully, there we go. What's the probability they make more than 8? Well, where's the cutoff for more than 8? That would be right here between 8 and 9. So everything over here is more than 8. And that means everything on this side, the 8 and everything less, is 8 or fewer, which is its complement. And so what this tells me is that we can use our rule of complements to figure the answer out to this one. If I want to figure out what's the probability that they make more than 8, so what is the probability that x, the number of shots they make, is more than 8? Well, that's going to be equal to 1 minus the probability that the number of shots they make is less than or equal to 8, which is its complement. This is our rule of complements. X greater than 8, that's this region over here, is the complement of x less than or equal to 8, which is this region over here. We already found this number. The probability that x was less than or equal to 8, didn't write it down, but I'm copying it from over here. It's this number right here, 0.492-ish. So if I subtract 0.492 from that 1, I'm going to get 0.508. And that's going to be the answer to this one. We have to use our rule of complements, be a little bit clever about how we put things together. So basically, if the question asks what's the probability that x is exactly equal to some value, you will do this with false for whether or not you're using a cumulative distribution. If it asks what's the probability that they make less than or equal to a given number, so 8 or fewer, that is the case where you would use true, that you are using a cumulative distribution. And if it asks for what is the probability that they make more than a certain number, you're going to have to use the rule of complements along with the cumulative case. So it may help to draw this picture and put them together that way. Okay, last thing we need to answer. So I've got, let me just type it over here. The answer to C was 1 minus what we just got in, what is that, B11. Oops, I forgot my equal sign. Enter. Is that all I forgot up here when I tried to do this number? Did I do an equal sign? Maybe that's what was going on. So coming way back to this problem earlier where I said I was having trouble getting it to work the way I thought, let me just make sure that I didn't forget the equal sign. And that's all it was. I didn't remember the equal sign when I typed this in. So you absolutely can type in numbers exactly the way that I thought you could. Just make sure you get that equal sign when you type in the square root. Sorry about that. I just missed the equal sign. Hopefully you caught that. But if not, don't worry about it. Oops. Let's delete that. And let's come back down here. Okay. Back to this problem. Sorry to jump around there. Part D asks for how many shots should we expect this person to make? And these are answers that we don't need any special functionality in Excel for. We can do these on a basic calculator because we've recognized that this is a binomial distribution down here for, let's say, part D. If I want the expected value, which again I can use either of these symbols for, e of x or mu of x, mu sub x, it's simply equal to n times p. And the idea is if this person makes 84% of their shots and they shoot 10 shots, then I just need to multiply 10 times 0.84, and I will get 8.4. We can do that on the calculator. We could do it right over here. So I could just simply do equals 10 times 0.84. And there's the answer, 8.4. I expect this person to make 8.4 of their shots. What is the standard deviation of the number of made shots? That was also a nice compact formula that we had. So if I want the standard deviation of the number of made shots, when you're dealing with a binomial distribution, and again, these formulas only apply to binomial distributions. They don't work in general. But for binomial distribution, that's NP times 1 minus P. And so for us, we already found what n times p is. It was 8.4. So for us, that's going to be 8.4 times 1 minus p, 1 minus 0.84. And so we can plug that into either a calculator or we can do it here in Excel. I can do equals square root parentheses 8.4 times parentheses 1 minus 0.84. And extra parentheses to close it all. So this is basically the way that I would type in exactly what I have written here. 8.4 times 1 minus 0.84, and then take the square root of the whole thing, hit enter, and I get 1.159-ish. These have units of shots. So I expect them to make 8.4 shots on average. Obviously, they can't make 8.4 shots, but what it's saying is, on average, have this person shoot 10 free throws, record how many they make. It'll be a whole number, right? Maybe it's 7, maybe it's 8, maybe it's 9, maybe they make all 10. But we write that number down and then have them repeat it again. Shoot 10 shots, write down how many they make. Shoot 10 shots, write down how many they make. Shoot 10 shots, write down how many they make. Do that over and over and average the results. And our average of our results should be 8.4. This number, the standard deviation, is on average on any given one of their given attempts, how far off from the 8.4 would I expect them to be? So this is basically a measure of how consistent are they? How spread out are their results? And it says that it looks like it's going to be a little bit more than one shot off from this. So most of the time they're going to be making more like 9 or 10 shots or more like 7 shots instead of making this number close to 8.4. On average, they're about 1 shot off from this number. So it's giving us a sense of exactly how consistent a shooter this person is. So with all of this in mind, we use Excel and the binom dist function to calculate these first two. For part C, we just had to be clever and use the binom dist function along with the rule of complements to come up with this value, the 0.508. And for the last two parts, part D and E, we don't need Excel at all. You can do this on any calculator. We're just plugging into these two formulas. So it's simply, can you plug into a calculator? You can do it in Excel, but you can also do it on any scientific calculator. So hopefully this gives you some sense of how we can use Excel to answer some of these probability questions. It requires, again, a little bit of clever thinking, and it requires you to remember what the formulas are. It's a little bit trickier than doing it on the TI-84 calculator, but it's not too bad, especially if you have those formulas in mind. It's just us figuring out how to actually apply those formulas in a table in Excel. So good luck with this. Use this on the homework, and let me know if you run into any issues.